Okay, so welcome back. As I said in the announcement, I think I said that in the announcement yesterday. Turns out that problem on Wednesday is entirely YouTube's fault. So I have I don't know, like 110 lectures or something posted on YouTube, and that has happened twice. So it happened on our first day of classes this semester, and it happened on Wednesday. So hopefully that's something that's not going to happen too much again. But anyway, if it does, unfortunately, it's kind of unavoidable. So what I'm going to do is over the weekend, I will post a supplementary lecture, which I don't really want to call it a supplementary lecture because it is going to be your lecture 13. It's going to be just as important as any other lecture. But the reason why I didn't want to put this one as a lecture that was posted outside of class times is that this bit about determinants is important. So I wanted to do it during the live stream. So I will post another lecture over the weekend. It would be nice if you watched it before Monday's class, but the way it's gonna work is it's gonna be a bunch of examples, so you're not gonna be totally lost if you don't watch it before Monday's class. But I'm gonna try to post it hopefully by Saturday afternoon. So by tomorrow afternoon, it should be uploaded um, to YouTube. Discord. I mean, if YouTube, like, if this became a recurring problem, it seems like it's absolutely perfect today, so there's no issue. But if it became a recurring problem, then I would look into other things. I really don't want to use Zoom, but I might have to use Zoom if that was the case. But anyway, so the problem is I think Discord lectures are maybe no good because I think there's some limiting like I would need to get some kind of like Discord premium account or something. And actually, I'm not sure Discord even supports above like 100 people or something. Anyway, okay. So determinants. This was the thing that we hinted at when we talked about inverses of matrices. Before I start, I was going to say your next homework will be posted, as I said at the beginning here in the chat. So your homework will be posted. Sometime like this afternoon sometime, so it'll be due next week, maybe next Thursday or Friday, which will include problems both from chapter 2 and from chapter 3 that we're starting on now. So chapter 3 is really short, so it is determinants. There's only a couple sections here. The determinant is going to be the thing that determines when a matrix has an inverse. Okay. The trickiest thing about determinants is computing them. Okay, so what I should say is that it is a very tricky thing to define because its algebraic definition is something that seems to come out of nowhere. And when you ask me a question like why does the determinant do the thing that it does, the answer is of a form you're probably not going to like, which is that the determinant is an alternating sum of things. Okay, alternating meaning it's a sum of terms, and the entries in the sum go plus minus plus minus plus minus. Okay, now that doesn't mean that each of those things are positive then negative then positive then negative. It's just that the actual operation itself, whether it's addition plus or whether it's subtraction minus, that is what's being alternated. Okay, you might compute a determinant and it have nothing but positive terms in that plus minus thing, but the operations themselves are plus minus plus minus plus minus. So that's an alternating sum, and it turns out that alternating sums tend to have nice algebraic properties, and it's because they have those nice algebraic properties that the determinant does the thing that it does. So that answer is not that satisfying for why the determinant is kind of a magical thing. So we kind of have to go backwards here, where I'm going to define what the determinant does. Your questions about why it's so magical will be dispelled by me just saying, well, like this definition has a lot of nice algebra stuff in it. You just can't see it, like, obviously directly. Okay, so I need some. First, I need. I need some background notation. Okay, I have to come up with some background notation for this to make sense. Okay, And so, what is the idea? Okay, so the idea is that if I start with a 3 by 3, maybe rather than actually write this out, I think I'm just going to show you the entries in the book where this is computed. So let me make this unblurry. Okay. Maybe I'll write the matrix itself here. So if I start with a 3 by 3 matrix, so A11, A12, A13, A21, A22, A23, and A31, A32, A33. So if I start with a 3 by 3 matrix like this, and I begin row reducing it, completely in general, right? I try to row reduce this completely in general. Okay, so let's see how this would go. So now I can actually write this out here. Okay, so this matrix that I have written here, when I scale each row by A11, I multiply every single entry by A11. Okay, I've done that. That is row equivalent. And why do I do that? I do that so that I can use A11 to zero out the entries below. Okay, so you don't worry if you're not like 100% following this. Like this is the intuitive explanation for what's going on. This is not something you don't have to reproduce this when you're computing determinants. Okay, and so here, so A11 is used to zero out the entries below it. Okay, when you do that, of course, you're subtracting here the first row times A21, for instance. So these are the entries you get once you've done those two row operations. So now we keep going. We now use this entry, or the A12 entry, to zero out this entry here in the third row, second column, so that when I do that, right, what I get ultimately is the following matrix. Okay, so there are zeros in these nice, convenient places, and in this last entry, I have A11 times delta. What is this delta? Delta is blah, this just complete mess of terms. Okay, so delta is that entire terrible mess of terms. Okay, now since A is invertible, this delta has to be non-zero, because if this delta were zero, I would have a row of zeros in my matrix A, which by the invertible matrix theorem that we went over last time would mean that A is not invertible, right? But A is invertible. We're starting with an invertible 3 by 3 matrix. Okay, and so if this thing is going to be invertible, delta has to be non-zero. Okay, so delta being non-zero tells us that A is invertible, looking in the other direction. So conversely, if delta is non-zero, A is invertible, so long as A11 is not zero here either. And so it turns out this delta is the thing that is going to be the determinant of that 3 by 3 matrix. Okay, but to see where this comes from, right? So that's the intuition behind defining the determinant in this way. But to see where this comes from, I need some notation. Okay, and so let's look at the following. So we already saw that for a 2 by 2, so that is A, B, C, D. Okay, the determinant, if this is my matrix A, then determinant of A we defined to be AD minus BC. Okay. For a 1 by 1, that is a matrix A that is 1 by 1, but that's just the single real entry A, the determinant of, if I'm calling this my matrix A, the determinant of a 1 by 1 is just that entry, whatever that entry is. Okay. Now, maybe it helps you to see that I can rewrite this A using the same notation that I usually use in general for a matrix. So let's say A11, A12, A21, A22. So I can rewrite the determinant of A for a 2 by 2 here as A11 times A22 minus A12 times A21. That's another way of writing my 2 by 2 determinant. Okay, so for 1 by 1s, that's completely trivial. You don't really need to even worry about this. For 2 by 2s, the most important thing is that we already know what the determinant is. We've defined it to be like this. Okay. All right. So, what about for 3 by 3 and higher? How do I do this? So some notation. Okay, so what's some notation? Let A be an n by n matrix. A, this is capital A sub ij, not little a sub ij. So big A is equal to a matrix filled with these little entries that are little a sub ij, right, where I and j go from 1 to n. When I write big A sub ij, what is this? This is the n minus 1 by n minus 1 matrix obtained from A by deleting the ith row and jth column from A. Okay. Now, for those of you that have seen the determinant defined before in some way, or if you've had Calc 3, you have computed determinants of 3 by 3s before. Okay. And so you might see where this is going. Okay. And so, in that case, what is my determinant? Okay, so definition, and this looks really, really ugly. Okay, so definition, the determinant of an n by n matrix. We will not talk about determinants for rectangular matrices because they don't really exist. Okay, so determinants are only things we talk about for square matrices. So the determinant of A sub n by n. So if A m by n is written in the usual way, so it has entries little a sub ij, then determinant of A is the sum of n terms of the form plus or minus A sub 1j times the determinant of A sub 1j. Right, so this is using my notation here where I have removed the first row and jth column from A. Okay, with plus and minus signs alternating. Okay, where the entries A11, A12, A13, and so on, all the way to A1n, are from the first row of A. So this is explaining what it is that's going on rather than me just slapping down the definition. Okay. Don't worry about a sub ij if n is equal to 1. So yeah, if n is equal to 1, we're not even dealing with matrices anymore, so we really don't care about it. In fact, this definition is something that we only do for n greater than or equal to 2. Yeah, so we don't have to worry about that kind of thing. Yeah, so when n is equal to 1, we basically consider it as we don't even have a matrix. But it's nice to know that you could build it up from that if you really wanted to. So the determinant of A is A11 times the determinant of big A11 minus A12 times the determinant of big A12 plus, and so on, all the way out to the nth term, which is minus 1 to the n plus 1 times A1n, the determinant of a big A1n. Okay, which can be written as the sum from j equals 1 to n of minus 1 to the 1 plus j times little a sub 1j times the determinant of big A sub 1j. Sorry. Okay. Now, seeing it in this form might not be that useful to you because this seems, so abstract to see it written out like this. Okay. And so, what is it that this is actually saying? So, first of all, some notes. Note, this is recursively defined. We'll talk more about that later because computing the determinant like this in general is computationally kind of horrific because of what it requires you to do in terms of the operations that you would have to do here. So this is recursively defined, i.e. to compute the determinant of a 3x3 matrix, I only need to know how to compute the determinant of a 2x2 matrix. Similarly, to compute the determinant of a 4x4 matrix, I only need to know how to compute determinants of 3x3 matrices. To compute the determinant of a 5x5 matrix, I only need to know how to compute determinant of 4x4 matrices. So once we define the determinant of a 2x2 to be what we did, then we can immediately, using this definition, generate what the determinant of a 3x3 is. We can use that to generate what the determinant of 4x4 is, and so on. So this is recursively defined. It builds up, maybe I shouldn't say, recursively here. I should say inductively defined. But anyway, so this is the idea. The idea is that we know what the determinant of a 2x2 is, so now we can compute determinants of 3x3s. So to see that, the best way to deal with the ugliness of this expression is to just start doing examples. Okay, because we're going to see a lot of tricks that allow you to compute determinants of arbitrarily large matrices if everything works out nicely. So this gets computationally awful as the size of the matrix goes up. And so for that reason, when you're asked to compute a determinant of a matrix, it's typically, if it's a completely general matrix, it's typically no larger than a 3x3. Okay, but I will give you examples of like 7 by 7 matrices you will compute the determinants of, but they are special matrices, so you'll be able to do it in a much easier way. Okay, so let's see what this is, and I'm going to be bringing that back to refer to what I'm doing here. So here's an example. Let A be the following matrix. So reading row-wise, 1, 5, 0, 2, 4, minus 1, 0, minus 2, 0. Okay. All right, and so what is the, so find or compute the determinant of A. Okay, so by the definition, right, what is determinant of A for a 3 by 3? So by definition, let me fold my paper here, right? So here's my definition, right? So by definition, this determinant is given to me by this formula. Okay, so then determinant of A is A11 times the determinant of big A11 minus A12 times the determinant of big A12 plus A13 times the determinant of big A13. And that's it. I end here, right? Because A is a 3 by 3, and so when A is an n by n, I have n terms here. So A is a 3 by 3. This has 3 terms. So this is my definition. Let's look at this, right? So remember, when we have a matrix written like this, this is what we're thinking of. This is A11, A12, A13, and then stuff below using the same subscript. So these are the entries in the first row, right? So rewriting this, this is A11 is 1. Okay, so A11 is 1 here, times the determinant of what? So it's the determinant of a matrix, but what matrix? It's the matrix big A11, which is the 2 by 2 matrix I get from, let me get 2 more pins here. So this is the 2 by 2 matrix I get from deleting the first row and first column of matrix A. So there's first row deleted. Oh my God, there we go. There's first row deleted. There's first column deleted. So the matrix that is left is 4, minus 1, minus 2, 0. So this is 4, minus 1, minus 2, 0. Okay. Minus, notice this minus sign is here regardless of what A12 is. So what is my point? A12 in this instance is 5. Okay. Now, maybe A12 is minus 5. And in that case, what goes here is minus 5. The point is this minus sign is here from the definition of the determinant. That's the determinant being an alternating sum. If this were a determinant of a 4 by 4, it'd be plus, minus, plus, minus. Okay. So this is minus 5 times the determinant of the matrix A12. Okay, which is what matrix? So the determinant of the matrix A12, or what is the matrix A12? I delete the first row and second column. So note, in this definition of determinant, in these sub-matrices I'm getting, these A sub ij's, I'm always deleting the first row in this formulation. So there's first row, second column, deleted. Okay, so I get the matrix 2, minus 1, 0, 0. So this is determinant of matrix 2, minus 1, 0, 0. Okay, and then lastly, plus A13, which is 0, times the determinant. I'm going to write it out. Normally I would stop here because I don't care. It's 0 times something. But this is 0 times the determinant of A13, which is the 2 by 2 submatrix I get from deleting first row again and third column. So this is the matrix 2, 4, 0, minus 2. So actually writing this out, this is 1 times the determinant of this matrix is 4 times 0 minus 1 times minus 2 minus 5 times the determinant of this matrix, which is 2 times 0 minus 0 times minus 1, and plus 0 times 2 times minus 2 minus 4 times 0. Okay. And so what do we get here? So this is 0 times 0, so that's 0. This whole thing is 0. So I have 1 times 0 minus 2, so this is minus 2. And so the determinant of this matrix A is minus 2. Now, what is determinant of a matrix measuring? Determinant of a matrix is measuring whether or not the matrix is invertible. But this measurement is done in a completely binary way, as we'll see. Okay, so there's no kind of sorta invertible, really. It's either invertible or it's not. Okay. All right, and so here is the thing. Question. Since you've probably seen this in some other context, but maybe you haven't. So, question. The definition of determinant expands across the first row. What do I mean by that? Well, let's go back to our example. To compute this determinant, why we call this expanding across the first row is the first row entries were my coefficients on these determinants. So 1, 5, and 0, 1, 5, and 0 were my coefficients on these determinants. And so I'm expanding across the first row, and because there's 3 of these columns and rows, I get plus, minus, plus. If this were 4, it would be in the same way, but it would be in terms of it would be 4 terms, and each determinant computed would be a determinant of a 3 by 3. Right? So you see how this would quickly blow up in annoyance, because to compute the determinant of a 3 by 3, you have to compute 3 determinants of 2 by 2s. To compute the determinant of a 4 by 4, you have to compute 4 determinants of 3 by 3s. So then to compute the determinant of a 5 by 5, you would have to compute 5 determinants of 4 by 4s. Right? So this gets really ugly really quick, okay, because of that fact. And yeah, this is the recursion nightmare. Geometric interpretation of determinant. It's too complicated to mention right now. The quickest way to think about the determinant is you came across a nice geometric interpretation of the determinant, which we'll talk about in another context later, which basically says that determinant is a scale factor. It's a scale factor in the context of if you have a transformation defined by a matrix, and this even works for transformations that are more complicated than ours. So for instance, take a transformation that is a mapping of the plane that's not even necessarily linear. So think about some kind of change of variables from Calc 3. Right? So a change of variables in Calc 3 might not be a linear transformation, but what did you do to compute the change of variables formula to be able to change your variables to something that was easier to compute? You computed something called the Jacobian, but what was the Jacobian? The Jacobian is itself a determinant, right? So that showed up in Calc 3 in that form. It's going to show up for us too in the more restricted case of a change of coordinates where the change of coordinate map is a linear transformation or a matrix transformation. So the determinant is the scale factor. You have a transformation that takes one region to another. How does it affect the area? The determinant. It scales it by the determinant. Okay, so that's the geometric, that's the quick geometric interpretation of what's going on here. Okay, so here, expanding across the first row is what I'm doing. Okay, it turns out that I don't have to do it that way. So, do I have to do this? Now, why would you ask a question like this? Well, you ask a question like this because, if we return to our example, the first row, the second row, and third row, they don't have exactly the same properties. What do I mean by that? They can be more or less nice, right? So in this case, the first row has 2 non-zero entries and a 0 entry. The second row has 3 non-zero entries, and the third row has 2 0 entries, only a single non-zero entry. What does that mean? Okay, what this means is if you could actually expand across some other row instead, you could take advantage of a judicious placement of zeros, right, to actually compute the determinant in a way that meant that you didn't have to do very many computations. So if you could expand across the third row, for instance, then 2 of these terms would have zeros as the things multiplying the determinants. So you would actually only have to compute the determinant of a single submatrix, right? The one corresponding to this entry, the non-zero entry. It turns out, not only can you expand across any row, you can expand across any column. This notion is called the cofactor expansion. So the answer to do I have to do this is no. We can use the cofactor expansion. The cofactor expansion formula for the determinant. So what is the cofactor expansion formula for the determinant? So first I have to define a cofactor. Okay. So definition, the ij cofactor of A, that's an n by n matrix with the usual terminology, is C sub ij, which is defined to be the number -1 to the I plus j times the determinant of that submatrix big A sub ij. This is the ijth cofactor. Okay, that's what this is called. Thus, by definition, for instance, I could write my definition of determinant in terms of the cofactors. So determinant of A can be rewritten now as, and I don't have to worry about minus signs here because that's taken care of by the cofactor expansion. So this, or by the cofactor definition. So this can be rewritten as A11 times big C sub 11 plus A12 times big C sub 12 plus all the way out to A1n times big C sub 1n. Now, you're going to complain here, right? That's your next word. You're going to say, wait, where'd the minus signs go? But I just said they're taken care of by the cofactor, right? They are absorbed in this cofactor term, right? So that's why this doesn't look like an alternating sum, but it very much is an alternating sum. Okay, I've just rewritten this in a convenient way. Okay, and so in this context, so we say that this is the cofactor expansion across the first row. That's what we call this expression. So what we have said then is that the definition of the derivative could be said to be written as a cofactor expansion for a matrix across its first row. Okay. The big important megafact Okay, that's why it gets 2 stars. It's a megafact, which is more true than just a normal fact. So a megafact here is, of course, it's not more true, it's just more important. So a megafact here is we can compute determinant of A via a cofactor expansion across any row or down any column. Okay, so this is extremely useful. This might be the most important fact that you learn about how to compute determinants in this course, although there's a warning that I'm going to give you for doing this, okay? So the warning I'm going to give you for doing this is computationally, this is absolute garbage. So I'll mention that at the end of what's going on. So what I mean by that computationally is doing this by hand, it is awesome because if you have a matrix that has a lot of zeros in it, it means you can judiciously pick and choose which row or column to expand across or down to compute the determinant. So if I give you a matrix that has a lot of zero entries, you could potentially compute that determinant of a pretty big matrix, 7 by 7, 8 by 8, 9 by 9. If I've put the zeros in the right place, it will work out just perfectly, kind of like a puzzle coming together, that the determinant you end up computing only requires you to like multiply a few numbers together. Okay? That's the nice thing about it. But those problems are certainly contrived. They don't have to be that way. So those are definitely contrived problems. And if I gave you a more natural problem, or if I even gave you the problem of, say, using a computer to compute the determinant of a 25 by 25 matrix, right? 25 by 25 matrix, that's not that big in terms of, you know, the types of computations that a computer can do. So in size-wise, that's not that big of a matrix. But I think that, and I'll mention this next time, a 25 by 25 matrix, if a computer used cofactor expansion to do it, it would take 500,000 years to compute, I think, even if it could do 1 trillion multiplications a second. So not great, right? Cofactor expansion is not great computationally, so there's other things that can be done there. But anyway, for us, cofactor expansion is going to be totally awesome. So this is the following theorem, cofactor expansion. Okay, so the determinant of a matrix A, which is an n by n matrix, can be computed via cofactor expansion across any row or down any column. So someone asked, do row operations change the determinant? Yes, they do. Not all of them. There's one that doesn't. So row replacement doesn't change. Row swapping changes. Row scaling changes. So yes, row operations change the determinant. Okay, we will get into that very much. That's actually what we're going to spend a decent amount of time on Monday's lecture, is what we'll talk about. So row operations change the determinant. So determinant of an n by n matrix can be computed via cofactor expansion across any row or down any column. The expansion across the ith row is determinant of A, which is written as A I1 C I1 plus A I2 C I2, and so on, all the way out to A IN C IN. Okay, and the expansion down any column, or down the jth column, is determinant of A, which is A sub 1j C sub 1j plus A sub 2j C sub 2j, and so on, all the way out to A sub nj C sub nj, to remind you, right, where C sub ij is minus 1 to the I plus j times the determinant of big A sub ij. Okay. So here's my expansion across the ith row. Here's my expansion across the, or down the jth column. Okay. Yeah, so the question is, should there be minuses? No, because this takes care of the minuses. Okay, in fact, how do you quickly compute these minuses? Note, to quickly keep track of minus 1 to the I plus j, think of the following matrix. So what we do to keep track of this is we think about a matrix. We don't know what size it is. It's some size. Whatever size it is, the first entry, what subscripts do we use to denote the first entry? So the first entry is little a sub 1, 1, right? So I is 1 and j is 1. So this is minus 1. So the associated cofactor, right, C11, would be the one that involves 1 plus 1. And minus 1 to the 1 plus 1 is minus 1 squared. So that's 1. So the term associated to the upper left entry is always positive. Right? Once you know that, you work outward, alternating. The next is minus to the right, and below it is minus. But then the next to the right and below is plus, which also means that this has to alternate, right? And so it alternates like this. This is how you keep track of those signs. Okay. So, an example for 3 by 3, this would be plus minus plus, which it exactly was, minus plus, minus plus, minus, and then there'd be a plus in the middle, right? So if you were to expand across the second row, the signs in the determinant sum would be minus plus minus. Now, when I say that, remember, I am not saying that means that you would have two negatives in your determinant sum, because that depends on what the coefficients are. Maybe the coefficients are negative. The point is that the operations coming from the definition of the determinant, whether it's a minus or a plus, that's what's being decided here. Okay, that's what's being decided. Right, exactly. It's just whether or not I plus j is even or odd. That's exactly right. Okay, but that is, you don't even have to think about that if you just look at a picture like this, and you're not going to be doing this for huge matrices or anything. So thinking about it in that way is only something you need to do, right, for conceptual problems. Okay, so let's actually do that example that we started with. Let's go back to our example. Okay, so we had the following matrix. So let me rewrite this matrix. So our matrix is 1, 5, 0, 2, 4, minus 1, 0, minus 2, 0. There's our matrix. So we did it across the first row by definition of the determinant. Let's do it down the last column. So going down the last column, what do I get? So I get that the determinant of A, by definition of cofactor expansion, so here's a reminder of what expansion I'm using. I'm going down the last row. Using this chart here, that means it's plus minus, or sorry, down the last column. So this is plus minus plus, just like for the definition. So going down the last column, determinant of A is equal to plus 0 times determinant. Just for practice, I'm going to write out what is that matrix that I'm computing the determinant of. So the matrix in question is the one I get from this matrix by deleting the first row, third column. So that is the matrix 2, 4, 0, minus 2. Again, it's not going to matter here because it's multiplying a 0. So now let's go, so this would be minus 1. All right, so this is minus 1 times, so again, this minus 1 doesn't get absorbed or anything. This is always going to be a minus, okay? Times the determinant of, so it's always going to be a minus going down the third row. If I go across or going down the third column, if I go across the second row, right, it would be minus plus minus. So here, this is going to be the determinant of what matrix? It's the matrix I get from deleting the third column and second row. All right, so third column, second row. So this is something that is different than the definition of determinant. So there's second row, third column is what we're deleting. So third column, second row. So 1, 5, 0 minus 2. So 1, 5, 0 minus 2 is that determinant. And then lastly, this is plus 0 times the determinant of the matrix I get. Well, I'm in the third row, third column entry. So I look at the submatrix I get from deleting the third column and third row. So 1, 5, 2, 4. Okay, again, if you were doing this, on your own, you wouldn't actually write out these things because once you see that they're multiplied by 0, you don't care. Okay, so these two things are 0, and then what do I get? I get minus 1, so that's 1, times the determinant of 1502, so that's minus 2 minus 0, so this is minus 2, just as before. Okay. All right. So why is this nice? Well, before we had to compute two of these determinants, but now using the fact that we're going down the third column, we only had to compute a single one of these determinants because the zeros were multiplying the others. Okay, we have enough time to do this example one more time. So let's go across the second row. So let's go across the second row. So determinant of A in that case is, we're going across the second row. Remember, it's a 3 by 3, so I have plus, minus, plus, minus, plus, minus, and plus, minus, plus. So going across the second row from the determinant, I have minus. This is always a minus in this instance. That means it doesn't matter what my coefficients are here. This sign is a minus sign. Okay, maybe this coefficient is minus 2. Then this would be minus 2. In this case, it is minus 2. So this is minus 2 times the determinant of what matrix? It is the matrix I get by what entry am I in? So I'm in second row, first column. So it's the matrix I get by deleting the first column and second row. So it is the matrix 5, 0 minus 2, 0. Okay, next, this is plus, right? So minus, plus, minus. So this is plus 4 times the determinant. What entry am I in? I'm in second row, second column. So this is the matrix I'm taking the determinant of here is the matrix that I obtain from this matrix by deleting the second row and second column. Right? So 1, 0, 0, 0. Okay, and then lastly, I get minus 1 times the determinant of what matrix? Well, what entry am I in here? I'm in the second row, third column. So this is the matrix I obtained from deleting third column and second row. So this is the matrix 1, 5, 0, minus 2. Okay. Oh, I'm off the page a little bit. There we go. All right, so now what? Notice, what's the determinant of this matrix? 5 times 0 minus 2 times 0. So this determinant is 0. What's the determinant of this matrix? It's 1 times 0 minus 0 times 0. So it's also 0. So what's left? This is minus 1 times minus 2, which is minus 2. Okay. So even here, even though that the coefficients were none of them were 0, some of these determinants themselves were 0, which was nice for us here. Okay. But note, it didn't matter in what way I computed this. Using cofactor expansion, I always get the determinant that I would get using any other method. Even just the definition of the determinant. Okay, expanding across the first row. Okay. All right, so I'll do more examples of this stuff in the lecture over the weekend. I will do a bunch of examples of that stuff, and then on Monday I will mostly finish our talk about determinants. So Monday will be pretty much the end of our talk about determinants, and then we will be moving on to chapter 4, which is general vector spaces, abstract vector spaces. I mentioned in the announcement yesterday that your first midterm will be coming up. So it's not next week; it'll be the week after. I think I had said maybe that Wednesday, or if not, maybe that Friday. I'll let you know over the weekend. I'll post when that's going to be. So like I said, your midterm is going to be it's going to be kind of similar to a homework set, but there's going to be some problems that you haven't quite seen in the homework, or might be some conceptual true-false stuff that you have seen in the homework in some way that you might need to dig up, or will be related to the true-false that you've done in the homework. So anyway, that's it's not going to be anything crazy. It will be very much mimic the homework that you've been assigned so far. So anyway, that's the deal. So I'll post the lecture over the weekend. I'll let you know when it is posted, and YouTube will hopefully upload it within an hour or two after that. And then on Monday we should be done with chapter 3. So we'll start chapter 4. If not by the end of class Monday, we'll start that on Wednesday next week. So your exam will cover chapters 1, 2, and 3, and maybe the first little bit of 4. Okay. So that's yes, and homework 3 is also getting posted later today, actually. How much time do you get to submit the exam? It will be we'll say at least 48 hours, possibly a little bit more. So at least 48 hours. Okay. It'll be not next week, but the week after. So yeah, that's it. Will I post practice tests? No, because it's like a take-home test anyway. So a practice test it's basically going to be the same thing, pretty much. Anyway, okay. So that is the deal. So anyway, I will see you all next week. I'll see you all on Monday.